All right, I have something for you. It is. It's a 3-question mini exam, and it's due a week from today. Right there. You're on camera, though. Sorry. It's a 3-question mini exam. Let me pass it out first. Same rules apply.
Is that triple integrals?
There will be some triple integrals in there. Did I not put them here? Eric, you doing okay? Just worried about you. You doing all right? Okay. Oh, come on. I'm going to put a couple here. Okay, so let's just take a quick look at this. Everybody have it? All right, the first thing I just want to point out is that on number 1, it's 1A and B, and you do one or the other, but do not do both. I'm not offering bonus on this one. So don't be like, well, if I do them both, will I get extra credit? Just turn one problem in. That's all I want. Either 1A or 1B. Number 2, find a center of mass of a lamina. And I show you the lamina. It's 2-dimensional. And I give you a density function. So that's pretty much what we talked about last class. And then number 3, find the volume of the solid which lies within this sphere above the xy plane and below a certain cone. All right, so you might have more questions about this later, but let's finish up the material. Okay, this will cover up through 12.7, and we're only in 12.5. But I plan on covering everything. Hopefully we'll get through 12.7 today. We'll see. I know that sounds ambitious. All right, so this is where we left off last class. I had actually, example 4, I had suggested you do that on your own. That was the one where you were projecting a solid, a tetrahedron onto 2 different planes. But we're going to move on to example 5. So what we want to do is evaluate a triple integral, z dv, where E is the solid bounded by a cylinder and then some planes. So we want to evaluate this triple integral. So the first thing we want to do is try and draw what the region of integration looks like. And that region of integration will be in 2 dimensions or 3 dimensions? 3-dimensional, okay? Our integration region right here, E, what we're integrating over is a 3-dimensional object, and we need to see what it looks like. Because once we see what it looks like, then we're going to look at its shadow on the ground and see what type of region that is. And then that should help motivate how we go about addressing this. So let's try and draw this. I have a cylinder, y squared plus z squared equals 9. That cylinder should open down which axes? It should go down the x-axis because x is missing, right, from the equation. So if I just try and draw a quick sketch of what's going on here. Let's do it this way. I'm going to go x here, y, z here, and z here. If I'm just doing a quick sketch of the region, I know it's a cylinder that goes down the x-axis, something like that, right? And then I've got x equals 0, which is really what? This is the yz plane, which is what, this back wall, you could say, right? This back wall. So I really don't need to consider anything on my cylinder past the yz plane. So I could kind of imagine that my cylinder is cut off here in the backside. Do y'all see that? And then let's go with the easier of the 2 here, because I have 2 of these. Z equals 0 is the xy plane. That's the ground, isn't it? So that's the floor. And then we have y equals 3x. That's a plane. And if we were looking on the x and y axis, like we were looking in two-dimensional space, x and y, then y equals 3x would look like a line, wouldn't it? Like this? Could have a slope of 3. So what we can imagine is that line. Can we draw that line on our picture in three-dimensional space? It would be on the ground, right? It would be like this, maybe like that. Y'all agree? Now, this is a plane, though. I mean, it's an actual plane, but that's where it would cross through the ground, right? That plane would cut through that line.
Is it giving the restrictions to that little piece right there?
Which little piece?
This one right here.
Yeah, something in there. Yeah, so I'm going to redraw it. After you kind of get a sketch of what's going on, you try and redraw the entire thing in a better picture, right? That was just so I could brainstorm. I think what's happening here is this plane, when it cuts through the cylinder, it's creating like this slice. This is what you're saying, right? Like this. And I'm getting some little piece like that. Do y'all see that? The back wall, that's x is 0. The ground, z is 0. This side right here, which is y equals 3x, and then this right here, which is the actual cylinder. So we got all those pieces together. So I'm going to redraw this. Now that I have a good idea what's going on, I'm going to do it like this. Here's y, here's x, here's z. So, oh yeah, also first octant. Sorry, I should have pointed that out. We're in the first octant only, which means that we actually have the xz plane. We can't go past that, right? So here's my piece. I've got the back wall of the cylinder. Where does that hit the y-axis? At 3. And then it hits up here at 3 also. That's because the radius of this cylinder is 9. I mean, the radius squared is 9. Right? So we okay with that? And then it comes out. Let's draw where that plane comes through the ground. Go like this. Right, there's that cut, y equals 3x. And then my cylinder would have continued this way, right? Parallel to the x-axis, would have come out this way. But that's going to get cut off right there. And then I'm going to have this, I don't know, all I'm thinking of is a slice of bundt cake. Y'all know, y'all have ever had a bundt cake before? Bundt cakes are hollow in the middle usually. That's what I'm thinking right now. It's a little piece of bundt cake. Am I the only one who's ever had a bundt cake?
No, I've had one.
Okay, you know what I'm talking about then, right?
It's hard to make when people don't make it.
Yeah, I don't know what it takes to make a bundt cake, but all right. Okay, so one of the biggest things for these problems is you got to get this solid, right? You got to get the region set up correctly. So I've kind of led us to this. I hope that you could have determined that on your own. You'll feel comfortable with that? Yeah, let's label some things here. The bottom of this thing is a plane, right? And that has the equation, what? Z is 0. Okay, that's the bottom. This side piece right here is another plane. What's the equation of that plane? 3x. Y is 3x. Now the back side of this thing, okay, this back side, I don't know. How do you say backside? How do I draw it? Because look, this piece right here is something, but the back side of that is something else, right? The back side. So what's that back side? X is 0. And then what is this curved piece right here?
The cylinder?
The cylinder, but how are we going to do it? How are we going to write it? Get it in terms of z. So solve for z on the cylinder equation.
So 9 minus y squared.
Square root 9 minus y squared. There we go. That's our solid. Any questions on that? I don't like this. It's backside.
So we're just taking all the restrictions and just...
Well, from this, we're going to try and set up our restrictions. So most of the problems that we have done are we take a look at the solid and we try and project it down to the xy plane. And we look at that projection down, like the shadow. So what's the shadow of this solid down to the xy plane? What does that look like? Looks like a little triangle. So let me draw it here. This is the projection onto the xy plane. I have x, I have y. It was this diagonal. It was y, not diagonal, but slope of 3, right? So y equals 3x. That's this line right here. Where does it stop at? What's this?
At 3.
Stops at 3, and that's a straight line across, right? So that's 3. Agreed? So we're talking about this piece here, this little patch of ground is this right here on the ground. And if we go back to double integrals, what type region is that? You could look at it as a type 2, but it's also a type 1. Because anything in this little red region, your x's are between two constants and your y's are between a constant and then a function, right? So you could say between two functions. What is the restriction on x, though? What's the biggest that x could be here? What's this value right there? 1. Because that's where 3x would hit 3, right? At x is 1. So I'm getting all those just by visual inspection, really. All right. So it looks like the shadow on the ground, the projection of the solid down to the ground is a type 1 region. And then as far as our restrictions on z, do we have a top and bottom surface? We do. The top surface is this, and the bottom surface is z is 0. Right? Okay. So let's set up all the restrictions on our variables. Here we go. X is between something, y is between something, and z is between something. And these will be our limits of integration for our integral. So what do we got? On x, it's what? 0 to 1. On y, it's the bottom function, right? First, so 3x to what? 3, the constant 3, right? It's going to always be 3 on the top. And then what about z? 0 to the square root of 9 minus y squared. There we go. And now we set it up. So the actual triple integral will be, first our restrictions on x, so 0 to 1. Then on y, 3x to 3. Then on z, 0 to root 9 minus y squared. And what are we integrating? Z, because that's what was given, right? So z, d, z, d, y, dx. That's it. All right, do you want to work through this? Yes? Yes.
When you're integrating, do you always choose the variable that it gives you? Like, do you
When you're
always start,
integrating?
like, since it's a z variable, you start with dz.
Oh, why we started with z first? No, the reason I chose z had to do with this. Okay, the x was between two constants, so that has to be the outer integral, right?
Okay.
Right?
Okay, I see it.
And then with the inner one was because our shadow on the ground had x and y in it, right? So y would be the next variable, and then z is where our two surfaces are between. Yeah? All right, so yeah, let's go ahead and work through this. We might at some point say we can take it the rest of the way, but let's just work through the beginning parts of this. All right, so the first thing I'm going to do is integrate that, right, with respect to z. So I'm integrating this with respect to z. What's the antiderivative of z with respect to z? 1/2 z squared. So integral 0 to 1 is the outer integral. The inner or middle integral is this one. And then the inside integral is now 1/2 z squared. And I'm evaluating from where to where? 0. So z equals 0 to z equals square root of 9 minus y squared. I'm going to figure out what that is, then I'll integrate with respect to y, then figure out what that is, and then integrate with respect to x. So when we plug in for z, when we replace this in here, that's good, right? because the square and the square root, that's going to go away. So you're just going to have 1/2, then 9 minus y squared, right? In parentheses. And then when you plug in 0, it's gone. So that's good. I like that. So this is equal to integral 0 to 1, integral 3x to 3, and then 1/2 9 minus y squared dy dx. That 1/2 is a constant, right? That can come out of both integrals out to the front, right? Let's go ahead and do that. So I have 1/2 integral 0 to 1, and then now the middle integral, antiderivative of 9 minus y squared is going to be 9y minus 1/3 y cubed evaluated from y equals 3x to y equals 3. And I've got to figure that out, then integrate with respect to x. So unfortunately, this one's going to be a little more computational because it's not 0 in there. So let's go ahead and do this. We've got 1/2 integral 0 to 1. And then now I'm going to plug in, I'm going to have 2 pieces, which I'm going to have to subtract, and then dx. So that's the way I'm going to do it. So 3 first, so 27, and then minus 9, which is 18. So 18 here. And then when you plug in 3x, you've got 27x. And then plug in 3x here, you're going to get minus 9x cubed. Yeah, 9?
Yes.
9x cubed.
You can factor out the 9.
Yeah, you could pull a 9 out at this point. I'm going to do something real quick because I notice I cannot combine any of these together, right? Like there's no like terms. So I'm just going to get rid of the parentheses here. That's going to become a minus. That's going to become a plus, and then like that. Is that all right? And then you're integrating that with respect to x. So when we integrate that with respect to x, we have 1/2, and then 18x minus 27 halves x squared plus 9/4 x to the 4th, and we're evaluating that from x is 0 to 1. Yes? All right, now when we plug in 1, we're going to get numbers. When we plug in 0, everything's going to go away, right? So all we really have to do is plug in 1. So if I plug in 1, I get 1/2, and then I've got 18 minus 27 halves plus 9/4. I think we can get a common denominator here. So I multiply everything by 4, right? So what do we get? Or not everything by 4. Is this going to be a nice clean number? I think it is. Okay. 72 minus 30, 40, 54 plus 9 over 4. I think it's going to be nice. Is it 24? Is that 24 on top? I'm not doing any math right now. I'm just waiting for you to do the arithmetic. What?
27 over 8.
27/8? Oh, I thought it was going to be nice. Is it 27 over 8?
54 plus 9 is 63. 63 minus 72,
9? Yeah, so that doesn't seem right. 9, what is it?
904 times
9/8. I don't even know. Seriously, this is arithmetic at this point. My brain really just doesn't want to do it. Now you have to do it, but I already done enough arithmetic.
27 over 8.
Yeah, I got 27.
You got 27 over 8?
Yeah, it's negative.
Oh my goodness. Okay.
Yeah, it's 72 minus 54.
It's Yeah, but, all right. Well, the thing is, I have the computer did it for me.
Well, it's 18 plus.
Let me see here.
9, right?
Did I not have the computer do it? I thought I had the computer do it. All right, I'm not going to do it. 27 over 8?
Yeah.
All right. I think if enough of us agree that it's 27 over 8, then it has to be 27 over 8. Good? I mean, all the hard work's done already. All right, that would be the triple integral of z dv. What does 27 over 8 mean?
Who knows?
I don't know, right? It depends on what it is we're integrating, right? This could be a lot of different things, depending on the context of the problem, which we have not talked about in the applications yet, right? We said that when you do double integrals, that you're really trying to find like volume between two surfaces, but when we do triple integrals,
Can't find anything.
can't talk about volume anymore. So, all right, moving on. That I talked about last class. This was just saying that you could project it onto different planes. I don't know why it's twice in the notes. All right, here's your favorite. Remember I was going to whip everyone with the stick if they didn't remember this with double integrals?
It's 1.
We had from last 2 classes ago or whatever it was that if you do a double integral over region D of 1 dA, that this is the area of D. So if you want to find the area of a region, you do the double integral over that region of 1 with respect to area, and that gives you the area. Well, it turns out that if you do a triple integral over a solid E of 1 with respect to volume, that gives you the volume of E. Yeah? Okay. This is kind of weird. If you use this same idea and go back to single integrals from Cal 1, then what is the integral from A to B of 1 like dx equal to? What is that? That's the length of what? The interval A from A to B. Because let's do this. This would be the antiderivative 1 would be x, right? And you're going to plug in B and you're going to plug in A. And that would give you B in first minus, then you plug in A, you get B minus A. Yeah? So if you look at that function, we're integrating from A to B. We're integrating the 1 function. This is 1. Then we did find this area, right? But that area was equivalent to the distance between A and B. So this is all again going. What I'm trying to get you to see is that integrating 1 with respect to volume, right, gives you the volume of the solid that you're integrating over. Integrating 1 with respect to area over D, right? D is 2-dimensional, gives you the area of D. So integrating 1 with respect to length, okay? Dx is length. Length, area, volume, right? Then if we integrate with respect to length, then this should give us the length of the interval we're integrating over, which is B minus A. It just goes all the way back. It's kind of weird. You never look at it that way back here, but now that we're here, you can kind of see it. It's pretty cool.
But that's only if you're doing it by 1. Right?
That's right, only with 1. Okay? The key to this is 1. In all of these, 1, 1, 1, 1. If you replace that with some function of x, then it's no longer the length. It's the area underneath the function. All right. So if we were doing that, if we want to use this concept, then we could ask ourselves this question. This is the same solid we just did, right? Same solid. What's the volume of that solid? What we just got, 27/8, was not the volume of that solid. It was not, because what were we integrating in that previous one? Z, right? But to do this, we want to go 0 to 1, 3x to 3, 0 to root 9 minus y squared, right? And what do we want to integrate? 1 dz dy dx. Now, unfortunately, this is going to be more difficult, because what made the previous problem easier was the fact that because there was z in here, we integrated and we got z squared, and it killed off our root, didn't it?
Yes.
And that was very nice, but this one just don't work that way. So let's walk through it a little bit. As you can see here, I say set up the integral, but do not compute, and that's because you're about to see how this integral looks. All right, so let's do this. 0 to 1, 3x to 3. Let's go ahead and do this antiderivative. The antiderivative of 1 with respect to z is just z. Now I'm evaluating that from z equals 0 to z equals square root of 9 minus y squared. And then I'm going to integrate with respect to y, then x. Were there any questions on where I came up with this? That's the same region, right? Except we're integrating 1 because we want to know that region's volume. All right, so we plug in this for z, and then we plug in 0. So all that really turns out to be is integral 0 to 1, integral 3x to 3. And then what we have there is square root 9 minus y squared dy dx, right? That's where we would be. And now we need to integrate 9 minus y squared, square root, sorry, of 9 minus y squared with respect to y. So how are you going to do that? Trigonometric substitution is the method you would use. However, that is a formula. There is a formula in your formula sheets. That's a common formula.
The difference of squares.
Well, it is a difference of squares, but it's under a root. So let's take the shortcut. We could do trigonometric substitution right now. All right? And on your take-home test, there might be some integration in there that requires a little bit of work. Just letting you know. So try and find I see you looking up formulas there. You see it there?
Yeah, that's du over square root of a squared minus.
This is not a fraction, though. It's not du over. It's just by itself. I think it's the bottom left. Hold on. Let me look. So everyone knows the number of the formula. It's going to be plus or minus. No, minus. There we go. Right there. A squared minus u squared. It's formula 30. Right? Arc sign. Do you want to do the trigonometric substitution, or do you want to just do the formula? Just do the formula. Y'all are so ambitious. Okay. So what is the formula? The formula says that if you have the square root of a squared minus u squared du, that it's equal to, what is it, 1 over a? U over a. U over a. Arc sine. Is this right? Are you there?
Yeah, I got u over 2.
Oh, u over 2. Okay. I don't have all 157 formulas memorized, so. Okay.
So it's u over 2 square root a squared minus u squared
Square root a squared minus u squared plus
square over 2
a squared over 2
arc sine
u
over a plus the your integral constant. So arc sine of u over a.
u over a. Okay. Plus c. All right. So that's the formula that we would use. So this would become integral 0 to 1. And then we would have this thing. But a for us is what? 3. All right. And u is really x or y. So this would be like y over 2 square root of 9 minus y squared plus a, which was 3. So 9 halves arc sine of u, which is really y over 3. And then we want to evaluate that from y equals 3x to 3. So then we've got to replace all of our y's with 3 and then all of our y's with 3x. Subtract. Ooh, messy, right? You can see why I said set up but do not evaluate? Yeah. Now, it could be done because if you had to integrate this, you could do basic u substitution on this. Like let u be this and the derivative of that's there. It's messy and time consuming. So Can we just now wave our hands at it and appreciate that the setup? Okay. So here it is if I just have my computer do it.
It's 3.
The answer is 3. I know, right? How does all that stuff become 3? It does. Yeah, there must be stuff that goes away. All right. So the volume of that little bundt cake slice was 3. 3 cubic inches, 3 cubic meters, 3 cubic feet. It depends on the units, right? It's a unitless answer here. All right. All right. Now, some applications. I'm going to give you the formulas. I'm not going to do an example. I'm going to leave you to do that on your own, because it's just an extension of what we've already done. So do you remember I had that cardboard that I was throwing around in class the other day? And I said the difference between homogeneous and non-homogeneous. So if we have a non-homogeneous solid, like, I don't know, the Earth. It's non-homogeneous, right? Different densities at different places. So if you have a non-homogeneous solid, and you know its density function. So the density function, rho of x, y, z, means you give me the x, y, z coordinate of the point, right, on the solid, and then it'll spit out the density at that point. If you know the density function, then the mass of that solid E is just the triple integral over the density function.
So that's how we kind of compute how objects in space, how much they weigh.
You could. You still have to know the density. I mean, that knowing the density function, that's a big deal.
I mean, like just in terms of like the Earth, kind of like,
You could estimate, okay, we think the core is this big, we think its density is this much, right? But there are probably more accurate ways of measuring the mass of the Earth than using that triple integral.
calculations with
Gravity, yeah. But that would give you the mass of the whole Earth. If you were trying to figure out mass of just certain parts, that'd be different. Okay, so if we can calculate the mass, then that means we can calculate the moments, right? So we have moments. The moments are different. We have moments about the YZ plane, moments about the XZ plane, moments about the XY plane. And the moments are they should look familiar to the moments we had from before. You're just adding a variable to the density function. You're adding x here, you're adding y here, you're adding z here. And that just becomes part of your integral. And why did we get the moments? What was the whole goal of getting the moments back with the laminas of two-dimensional laminas? Because we could get to moments of inertia, but before the moments of inertia, we used the moments to get the center of mass. So if you want to know the center of mass of that object E, you have to take x bar, you have to calculate the x, y, and z coordinates of the center of mass. X bar, y bar, z bar. The x coordinate is the moment about the yz plane, which is this one right here. It's that triple integral divided by the mass, which itself is a triple integral. So you got to do 2 triple integrals to do this x bar, right? You got to do 2 triple integrals to get y bar. You got to do 2 triple integrals to do z bar. Although the bottom ones you only have to do once, right? You have to get that number one time. So really it's a total of what, 4 triple integrals you have to do here to get x bar, y bar, z bar? And then you have the moments of inertia, and you have moments of inertia about the x-axis, y-axis, and z-axis. So here they are. These are all in the book. I'm just putting them up here, all right? And there's the homework for that section.
When you calculate the inertia like that, you write it as a triple, as an order triple? Or is it...
Your moments of inertia are going to be a number. Your moment of inertia is a number. That's all it is. X bar, y bar, z bar, that gives you a point on, well, it doesn't have to be on the solid, but it gives you a point that is the center of mass of that solid. So you could imagine that solid being a single point at x bar, y bar, z bar with the mass that you calculated. Moments of inertia just gives you, remember, it's a calculation of the amount of resistance to motion about a certain rotational axis. All right. So on the take-home exam, nothing I've said really, you're not going to be asked on the take-home exam to calculate the center of mass of a three-dimensional solid. I do ask you to find the center of mass of a two-dimensional lamina, don't I? With a non-uniform density function. So you have a non-homogeneous lamina here, and you're trying to find x bar. So that's from last class, not today. All right, we're going to move on. 12.6. All right. So we talked about in two-dimensional space that we have, in 2D, we have Cartesian, which is your traditional, you have a point out here, it has an x coordinate and a y coordinate. That tells you how far to walk out parallel to the x-axis, then how far to walk up to, right? And that's how you get to that point. That's our common, what everyone knows, right? Before you even walk into a pre-calc class, everyone's working in Cartesian. We talked about polar. Polar coordinates was the same thing, right? It's the same idea that you have a point in two-dimensional space, but how you get to it's different than how you get to it with Cartesian. So how do we do that here in polar? Angle and a radius, right? You say, okay, start by pointing. This looks like an eraser. Look at that. It's opposite day, I guess. Look at that. That's pretty cool. Let's see what this one is. If this one comes out red, we're all going home. No, okay, sorry. All right, so there's another point, right? So to do polar, what we do is we imagine, and this is an important subtlety, we always start at the origin, right? And we imagine we're pointing out the x-axis. That's where we start. Then someone gives us an angle to rotate by. So we rotate by some angle theta. And then once we're looking in this direction, then we need a radius, which tells us how far to walk, right? R. And that's how we get to that point. So with polar, there's two things you need to know, r and theta. With Cartesian, there's two things you need to know, x and y. So in two-dimensional space, the minimum amount of information you need to get to a point is two pieces of information. The x and the y, or the r and the theta, and you're there, right? You can walk out to that point. Yes? All right, now we're going to go and we're going to do the same thing, but now we're going to be thinking 3D. So in 3D, we have Cartesian, right? Cartesian, you have a point out here. So you go out x, y, z, right? You have an x coordinate, a y coordinate, a z coordinate, x, y, z. So you need three pieces of information to get out to that point, right? Another way we can do this is by using not polar. We don't say polar, okay? Polar is reserved for two-dimensional. But something equivalent to polar in three-dimensional is what we call cylindrical coordinates. And it works like this. Let's say I want to get out to that point. And I start here at the origin. Here's my x-axis, here's my y-axis. What we're going to do, and I think it's easier if I do it in the room than to do it on the board. Let me walk over here to the origin again. And then this is our x-axis and this is our y-axis, right? And this was our z-axis before. So if I want to get to the projector, I can walk out x this way, right? This would be Cartesian. X, and then y, and then up to z, right? To get up there? Okay, that's Cartesian. Cylindrical says this. Point out the x-axis, just like polar. Tell me how far to rotate, okay? And then tell me how far to walk out. Okay, so I will walk out, and I'm going to walk across the tables here. And now once I get to right below the projector from the corner of the room, excuse me, when I walk out that certain distance, then go up. All right? So I still need three pieces of information. I need to know how far to swing out. I need an angle to rotate through, theta. I need to know how far to walk out, r. And then once I get to that point, go straight up and let's just let that be z. So it's just like Cartesian. The z is still the z. But instead of using x and y to get there, you're going to use the r and theta that you used from polar. So all the r and theta do is move you around on the xy plane. And then the z just moves you up or down. So r theta here. Understand this is cylindrical. Now the question I think becomes, why do they call it cylindrical? Why did they call it cylindrical? So I have an animation that will help you see why they call it cylindrical coordinates. Do you understand the setup though? Okay. So that's why we say it's a 3D version of polar coordinates. Would you mind hitting, Eric, the light switch, far right light switch? Yep. Yeah, it's a matter of what happens. What do you start drawing if you hold two of your variables constant? So remember, we need a radius, we need a theta, and we need the z coordinate, right? This is a little too big. We need a radius. So what happens if I want to get to this point right here, right? I had to rotate by some angle, walk out a certain distance, and go up to z, right? And I'd be at that point. Now what would happen if right now I just let my theta start changing? Then that point's going to start moving around, isn't it? If I just let theta change, and I'm going to draw a ring around that thing, right? I'm going to draw basically a circle that goes through that point, something like that, right? That's what would happen if I start letting theta just change and holding my radius and holding my z constant. Yeah? What would happen if instead of swinging the theta around, let me move this theta back somewhere more reasonable, there we go. Instead, let's just start moving the, let's do the z. What would happen if I do the z and I start changing that? What am I going to draw? A line, right? Like this. And then I could change my theta a little bit and then start moving z again, right? And I would draw another line like this. And what I get basically is a cylinder, don't I? It's like a shell. Then if I start changing my radius, what happens? It becomes a solid, like bar, doesn't it? Like a true solid cylinder. And so that's why they call this cylindrical coordinates. Because in this coordinate system, if you hold two of your variables constant and let the other one move around, and then hold the other two constant and let the other one move around. So you take turns holding two constant and letting one move. You start drawing these cylindrical shells, and it just creates a solid bar. My beloved Calculus 3 professor called this planet Schlitz. Like, I guess he likes Schlitz beer, and he draws beer cans, so he called this planet Schlitz. You've got this cylindrical beer can shaped coordinate system. Yeah? Okay, if planet Schlitz draws cylinders, right? Cylindrical coordinates draws cylinders. What does Cartesian coordinates draw? Little three-dimensional though, right? So little boxes, right? So imagine if I'm back to Cartesian coordinates, if you hold, let's go out to a point here. If I hold two of my variables constant, like y and z, and let x move around, I'm going to go, let x move around. I'm going to draw like a little line segment like that. If I let y move around and hold x and z, I'm going to draw little line segments this way, like this. And then if I hold x and y and let z move up and down, then I'm going to start drawing vertical lines. And so what I wind up drawing are a bunch of little cubes. So you could say that Cartesian is like planet cube, right? It draws little cubes everywhere. You move around, and if you move around in Cartesian coordinates, you're going to be on edges of cubes as you move around. Always moving in straight lines parallel to these cube edges, right? But if you're on planet Schlitz, I still call it planet Schlitz, like second nature. If you're in cylindrical coordinates, then if you're moving around in this coordinate system, changing one variable, you're always moving on the edge of a beer can, whether it be moving around the outside radius of it, down the edge of it, right, or going into the can or back out. Understand? That's your... We can call it something else. Is there another beer we want to call it, or do you want to call it like some sort of exotic bottled water or something? Do you care? I don't care what you call it. It's cylindrical coordinates, right? To me, it'll always be Planet Schlitz, though. All right, so how do we do triple integrals with cylindrical coordinates? Now, let me try and explain what the value of cylindrical coordinates is. This solids, these triple integrals that we've had, these solids that we've been doing, these E's, right? The E is the solid. Every shadow on the ground has been a type 1 or type 2 region. We have been very careful to make sure that the solid on the ground was not something crazier. But what if the shadow of that solid onto the ground is not type 1 or type 2, like this? What if the shadow on the ground is a polar region, right? That's a polar region in two-dimensional space. So we have something like your thetas are stuck between two constants, right? Theta is stuck between alpha and beta. You've got your radius is stuck between two functions of theta. Here they're constants, but they could be functions. Then your z is stuck between two surfaces. Come on. Surface on top and surface on bottom. So the only thing that is changing now in cylindrical coordinates is the shadow on the ground is a polar, right? The shadow is polar. So when the shadow is polar, we use cylindrical coordinates because it just helps us draw that region better. Let's try to do an example. Oh, well, I didn't give you the formula. The formula, as you might imagine, would be that if we're in cylindrical coordinates, oh, you know what? I think I missed the conversions, didn't I? I missed the conversions back here somewhere. There it was. Oops. Just remember, with polar, it was x was r cosine theta, y was r sine theta. That was our polar conversion. And then the identities, the Pythagorean identity, and then the way we could get theta. That's all the same. It's the same exact from polar. And then how do you go from Cartesian to cylindrical with the z coordinate? You don't do anything. The z is still just z. So do you see why we're calling this like polar in 3D? Because everything is still polar. The only additional piece we have is that we have a z coordinate. So when we set up a triple integral, if we have a polar region on the ground, we get our theta between two constants, our radius between two functions of theta, and then our z coordinate is going to be between two surfaces. And notice that the surfaces, right, our z depends on x and y. Those x's and y's have to be turned into r cosine theta, r sine theta. So this looks pretty nasty, but it really, once we do an example, I think you'll see it's not that bad. And I think I accidentally highlighted that. Did I accidentally highlight that?
No.
No, I didn't. I just wanted you to remember this. Anytime you do polar, right, you must include the r. So it happens in cylindrical coordinates, you have to include the r. And back in two-dimensional double integrals, you have to include the r. Let's do one. All right, let's evaluate this triple integral. So I'm doing a triple integral of x dv. So this is not a volume, right? This is not going to give us the volume of E. This is going to be some other numerical value that means something. I don't know, maybe it's the center of mass of something. Who knows, right? Or not center of mass, maybe it's the mass of something. Okay, let's try and get our heads around this region here. The region is bounded by z equals 0, xy plane, right? That's the floor. Z equals x plus y plus 5, which is a plane, another plane, but it has some tilt to it, right? So we've got the ground, we've got some plane with some tilt, we've got a cylinder, x squared plus y squared equals 4. That's a cylinder that opens up which axis? Z-axis. It has a radius of 2. And this one, another cylinder opening up the Z-axis, radius 3. Let me try and draw this. I've got the ground. 100 markers in here, none of which work. I have the ground. This is a real rough sketch. Ground here. I've got a cylinder that has a radius of 2. I've got another cylinder, a radius of 3. And I've got this plane that comes through and cuts through all this stuff, right? That's basically what I've got going on. Do you see the solid that's basically bounded by all those? Can you visualize it? What does it look like? Like a what? It's a cut-off cylinder. So let's cut that cylinder off. What would it look like if I cut that cylinder off? It looks something like this. Like that. That's where it would cut through the cylinders. Yes?
It's
Like a Twizzler? That's been cut at an angle?
Yeah.
It's like a straw with a really thick wall to it. That's Twizzler, right? Do y'all see this? The ground has cut the bottom off, right? So you got the ground, creates one boundary. Inside this cylinder, it goes down, it's hollow inside, right? Then at the bottom, you got something like that, right? That's supposed to be the same radius, but yeah. That's our solid. And we are going to integrate over this region. Let's investigate the shadow on the ground. So if we try and project, light from the top down the XY plane, this thing is sitting on the XY plane, isn't it? So our shadow is actually where it touches the XY plane. So let's look at that. Here's our XY. What does it look like here? Two circles, right? We've got a circle here, radius 2, and then an outer circle, radius 3. And we're talking about this region right here, right? That's the shadow on the ground. Now that's good. I think we have some control over the ground, right? That's a polar region on the ground. Now we just need to take a look at this solid. Do you have a top surface and a bottom surface?
Yes.
What are they? What's the top surface? What's the thing that's cutting your solid off on the top?
X plus
Z equals x plus y plus 5. What's cutting off this thing on the bottom? Z equals 0. So this is a polar region. If it's a polar region, hopefully you can give me some restrictions on r and theta. 0 to 2 pi on theta. So we're to draw this region, we got to swing all the way around. So 0 to 2 pi. And what about the radius? 2 to 3. I was about to say, who leaves their markers in here that are half dead? It's me, actually. I keep on leaving them in here. I just stack them up, and then I move them, then I use them again and move them. And okay, that's your theta and your r. So we've got our region on the ground covered. Now, because we're in cylindrical coordinates, I just need a restriction on z, right? What's my restriction on z here? 0 to x plus y plus 5. Now, here's where we run into a little bit of an issue. If we're going to go to cylindrical coordinates, that means we're really doing polar, which means all our x's turn into r cosine thetas, all our y's turn into r sine thetas, right? So I'm going to have to come back in here and adapt this restriction. I've got to change my x's to r cosine theta and my y's to r sine theta. And within the integral itself, if I have an x or a y or a z in the actual integral, that needs to be changed over also. So everything's going to get switched. And we will be able to set it up. All right? So here comes the actual setup of the triple. So integral 0 to 2 pi, integral 2 to 3. Could I change the order of these? Could I do theta instead of theta as the outer one? I could. Why?
Because they're not stuck in between the functions.
That's right, because they're constants. Those two could switch places. But I'm just going to keep it the way we've done it. This will be d theta on the outside and dr on the inside. And that forces me to go dz here, right? Z is not going to change to anything. X and Y change, Z does not, because it's cylindrical, right? Cylindrical, Z is Z. All right, do you want me to put it now? I'm wanting to do it now. R, I want to put that R there so I don't forget about it. I mean, right? I'm doing that because I'm in cylindrical. There's got to be an R in the integral. All right, now let's get our other limit of integration here. It's going to be 0 to x plus y plus 5. So r cosine theta plus r sine theta plus 5. And what am I integrating? X, which is r cosine theta. Okay, this one's bad. I think these are all bad too. Well, this one looks good. All right, so we're really going to have r squared, right? Let's start going through this. Again, I might at some point say, you know what? This is why you're the student. You get to do this. I don't need to do this. But so you can appreciate some of the work it's going to take, all right? It's really time. We just don't have time to sit there and go through all these. It's the setup. The setup's the most important part of it, because if you get any of this wrong, of course, this doesn't matter anymore, right? All right, so we are going to integrate. Let me do that first integration. 0 to 2 pi, 2 to 3. And when I integrate this the first time through, this is r squared cosine theta, right? R squared cosine theta. And I'm integrating that with respect to z. So the antiderivative of r squared cosine theta with respect to z is r squared cosine theta z. Because that's like a constant. So r squared cosine theta z. And I'm evaluating z from 0 to r cosine theta plus r sine theta plus 5. And once I'm done with that, I'll integrate with respect to r and then with respect to theta. Questions on that? Z equals 0 is the easy one because it kills everything off, right? But now I've got to go in here, I've got to replace z right there with this, which means the r squared cosine theta is going to distribute to each of these, isn't it? So that becomes integral 0 to 2 pi, integral 2 to 3, and let me just go ahead and distribute that. So we're going to have r cubed cosine theta squared. So that was the r squared cosine theta times r cosine theta. And then what's the next one? Plus r cubed cosine theta sine theta. And then the last one, plus r squared, 5r squared cosine theta. And I'm integrating that with respect to r, then theta. Y'all see what I've done here? It's all right? Oh, man. So when I integrate this with respect to r, it's not going to be that bad, right? Because, you know, these things with